start. I introduce to you Ligabo from University of Bari, and she will talk about truncated quantum observables in their semi-classical living. So,
thank you, Mario, and thanks to Alessandro Ligabo for his kind invitation. So, as Mario told, I will talk about truncated quantum observables, and in particular, I will be interested in the semi-classical living of the dot. Okay, this presentation is based on two papers. The first one is a joint project with Fabio Kunde and Paolo Facchi, and the second one is with Fabio Kunde and Maria Caterina Susca, is a master's student. Okay, so this is the outline of this presentation. So first of all, I will introduce what I mean by truncated quantum observable, and then I will provide some physical motivation that motivate our study. Then, as I said, I want to discuss the semi-classical limit of this object, of these Hamiltonians. And so for this reason, I will introduce one possible way to compare quantum mechanics and classical mechanics, that is the phase-space description of quantum mechanics. Then I will provide some heuristic explanation of the results, so very basic, and then I will state our main theorems, rigorous theorem. Then I will present some examples, some models that we have studied, and finally, if I will have time, I will discuss also something about the quantum dynamics generated by this kind of truncated observables and the proper semi-classical. And finally, I will show you some of the problems that we are trying to address in this field. Okay. So what I mean by truncated quantum observable, I consider a self-adjoint Hamiltonian on a separable unified space and the family of orthogonal projections. I assume that of course p squared is equal to 3 and is equal to the adjoint, and I require that this family of projection is monotone. Okay, so the range of Pn is contained in the range of Pn plus 1. Okay, and also I assume that this family of projection is finite rank. Okay, so in particular, we assume that the rank of the orthogonal projection N is exactly N. Okay, so notice that I'm not assuming that these orthogonal projections are the spectral projection of H. So in general, I'm interested in the situation where H and Pn do not commute. Okay. So if I assume that the range of Pn is a subset of the domain of the Hamiltonian, I can construct what I call the Hn, so the truncation of H obtained by multiplying from the left and from the right H with this projection here. Okay, so this kind of object are studied in the mathematical literature in many settings, but what is the motivation for us to study this kind of object is related to a topic that I like very much, that is the quantum zero factor. So this kind of object are the so-called zero Hamiltonians, and I try to recall some basic definition of this kind of object. So what is quantum zero dynamics? So assume that we have a quantum system in a Hilbert space, and assume that the Hamiltonian of the system is H, and it generates a dynamics. Okay, we have the unitary group generated by Hamiltonian. Then we consider an orthogonal projection phi. What is the meaning of this projection? The meaning is to describe a measurement that we perform on the system. For instance, we can perform if the system is in a certain region of the space. Okay, so it's an orthogonal projection that we use to describe a measurement that we perform on the quantum system. Okay, and of course, this is interesting when the projection does not commute again. Okay, otherwise, the result of the measurement is straight. Okay? So we consider the following procedure. So we have a time interval from 0 to t. Okay, and we consider an interval n, and we divide this time interval in n subinterval with equal length t over n. This is t over n. And we start with the initial state at time 0, and we consider the evolution generated by the Hamiltonian for the first time t. So here we consider the evolution for a time t over n. Here, at time t over n, we perform a measurement of the system. Namely, we apply the projection. And we repeat the procedure again. If the outcome of the measurement is positive, we iterate this procedure. Here, it again apply the unitary group, and then again we project. Okay? So, if phi 0 is the normalized initial state of the quantum system, so we start with psi 0, we apply this unitary group, then we project. If the outcome is positive, we again consider the evolution for another t over n, and so on. We repeat this procedure n times. So at the end, at time t, if all these measurements are a positive outcome, we obtain a state that is up to a normalization given by this vector. So, and this vector is obtained by applying this product formula to the initial state. Okay? This is a product formula that is not so different with respect to the proper product. Okay? So, and what is our interest? Is to send this number to plus infinity. So, we want to look at the system when we perform very frequent measurements in the time. Okay? So, what is the result? Under suitable assumption on the Hamiltonian and on the projection, we'll obtain that this product formula has a limit. This is a unitary group with an Hamiltonian that is called the zero Hamiltonian that has this form. So it's obtained by multiplying the Hamiltonian, the original Hamiltonian, from the left and from the right with the projection associated to it. Okay? So what is surprising is that the evolution generated by H wants to let the state of the system escape from the range of the projection. But if we measure very frequent, we are able to confine the state of the system in a proper subspace of the space, because the dynamics becomes unitary in this subspace. So the Zeno procedure produces an hard wall on the unit space. Okay? Okay. So recently, there has been an experimental proposal for generating quantum xenodynamics, a multidimensional quantum xenodynamics. What I mean with the multidimensional xenodynamics, I mean that the arc of the projection that describes the measurement is strictly larger than 1, because all the previous experiments about Zeno effect was with the rank 1 projection, one rank measurement. Okay, so in 2010, these physicists proposed a quantum electrodynamics experiment for producing a quantum xenodynamics using the cavity at the polynormal superior, and the mathematics. So I mean, the model was this one. So in the cavity there is an electromagnetic field, and the evolution of the field is generated by given by the displacement operator that is essentially is generated by the moment. So there is an injection of photons inside the cavity, so the number of photons try to increase, want to increase. And the projection is pi n. That is a projection over the first n eigenfunctions of the harmonic. So in essence, the measurement associated to Pn asks to the cavity if the number of photons in the cavity is less or equal than n. So there is an injection of photons, so the number of photons want to increase, but the measurement asks, are there less than n photons? And using this procedure, they are able to give a bound of the number of photons in general. Okay? So what is the Zeno limit here? So pi n is the sum of k from 1 to n of uk in direct notation, where uk are the Hermite function, the eigenfunction of harmonic oscillator. And h is the momentum. So the Zeno Hamiltonian is exactly a truncation of the momentum operator in the eigenspace of the first n Hermite eigenfunction. Okay? So this is an experimental proposal that works and that has been observed. Okay? So inspired by the Nobel lecture given by Sergio Roche, that is one of the physicists who proposed this experiment, in which in the Nobel lecture he discussed how controlling photons in a box is a way to explore the quantum to classical boundary. So we ask the following question. So what is the semi-classical limit of this quantum Zeno dynamics? But the point is that quantum Zeno effect at the same level of tunneling is a purely quantum phenomenon without classical approach. So it vanishes at all orders in the constant H bar. So it's a tricky question. Okay. And so for this reason, I want to explain what I mean with the semi-classical limit of this quantum Zeno dynamics. So first of all, I recall you that I need a common language to compare quantum mechanics and classical mechanics. And one choice is the quantum mechanics described in classical phase space. So quantum mechanics is taken in Hilbert space that here we can assume is L2 of R, okay, for simplicity. While classical mechanics is described in phase space, that in this case is R times R, okay? Now, in quantum mechanics, observables are operators, central joint operators in that space, and to this operator we can associate, for instance, the integral kernel, and we given an operator T, we can associate an integral kernel exists. And similarly, we can assume, we can define what is the by symbol of an operator in terms of sort of translation and partial Fourier transform of the integral. Similarly, if we have a function in phase space, on phase space that is a classical observable, we can quantize using biquantization. And so we have a map that transforms operators in classical observables. Okay, there is a one-to-one correspondence. And this is the definition of the by operator of the classical observable. Okay. Then operators in quantum mechanics are not commutative generally, while in classical phase space observables are commutative. So we need a way to include this non-commutative product in phase space, and it is given by the Moyal product. So given two operators T1 and T2, and given two by symbols sigma 1 and sigma 2, we can define the product of these two symbols simply considering the by symbol of the product. Okay, and this product is not commutative; it's a product that depends on each bar, but depending in a nice way, as one would expect. So when H bar tends to 0, the Moyal product between them becomes the one-wise. Okay. Finally, states. states in quantum mechanics are, for instance, normalized at vectors in that space. In classical mechanics are points in space or density in space. So there is this definition of Wigner transform that associates to a vector in L2 an almost probability, joint probability measure between position and momentum. That is the so-called Wigner transform of psi. That is, how to say, the Wigner transform really wants to be the joint probability distribution, but the joint probability distribution cannot exist by the Heisenberg uncertainty principle. But we have that this object has the right marginals because the integral in dp is the position density, the integral in dx is the momentum density. It is normalized as total mass equal to 1, but of course, it is not possible. Okay, so now that we have a common language to describe in the same space quantum and classical mechanics, we come back to our problem. So we, as I said, consider an operator L2 and a family of projection, monotone family of projection, and we consider the Hamilton, the Zenon. Okay, so the Hamiltonian obtained by multiplying on the left and on the right the second operator with this. And we can consider, of course, the Y symbols sequence of the projection and of these truncated oscillations. And we ask, okay, what happens to these sequences in the same classical limit? For instance, when H bar tends to zero. Okay, so let us look for in the beginning to the projection. Okay, so the projection can be represented as in the harmonic oscillator case as a sum with the k that goes from 1 to 1 of this rank 1 projection, where UK is a certain orthonormal basis of the units. Okay, and so since this object has a trivial kernel, we can compute what is the bisymbol of this object, and this bisymbol is in L2 and is in C0, and moreover it is very easy to compute what is the L2 norm of this object. That is equal exactly to square root of 2 pi h bar. So of course, if we consider directly the limit h bar to 0, this is a trivial behavior because everything tends to 0. So something interesting can emerge when we send simultaneously h bar to 0 and n to infinity, keeping fixed to a certain value. Oh, and this is exactly what I mean in my presentation for semi-classical. Okay, now sort of a heuristics argument of what happened in the limit. So, as we noticed, this sequence is bounded in L2. Okay, it's a constant. All the L2 norm are constant. And so it needs up to a subsequence, a certain limit. Okay, that we call C. So, since the projection is equal to the projection squared, the 2 by symbol must coincide. But the symbol of P squared is the Moyer product of Pn, sigma Pn times the Moyer product sigma Pn. And this, in the semi-classical limit, we, in a certain sense, expect that is the pointwise. So is sigma Pn squared. Okay? So if the limit exists, it must satisfy that sigma is equal to sigma squared. So we expect that if this limit exists, the limit can be or 0 or 1. And so we expect that this is the characteristic function of a bounded region. Okay. And okay, so this is very informal, what I said, but this informal discussion can be made precise when, for instance, pi n are the spectral projection of suitable Schrödinger. Okay, I will come back later. So here, I just want to give some heuristic explanation. So let us now look at the Weiss symbol of H. So we consider for now only Hamiltonians that have the Weiss quantization of a certain function f. This is just because in this case the Weiss symbol and the principal symbol coincide, so the situation is more under control. And so if we look at this object, this is just Hn, because it's Pn, this is H, and this is Pn. So the Weiss symbol, so what we do first is to commutate these two vectors. So we split this in f of f times Pn plus the commutator. Okay? So since we expect that the algebra of observables is commutative in the limit, so we can neglect very risky. I will come back later to this point. At the limit. So we expect that this doesn't contribute very much. And then this is just the Moyal product. But the Weiss symbol of the quantization of f is f. So this Moyal product is just f times this at the first order, because the Moyal product is almost the pointwise product in the limit and the same classical limit. So if this object has a limit sigma, so we expect that at the end the Weiss symbol of Hn, so the truncation, go to f times the limit of the function. So this is very rough, okay? I agree with you, but this is very rough. But this is exactly what I want. Okay? That all these are true. Okay? Of course. Okay, so first of all, let me give you which are some possible assumptions that we can make on the projection and on the Hamiltonian in order to guarantee that all these approximations hold. So fix mu larger than 0, and we assume I state several assumptions that we may ask on these two objects, the projection and the proof. So condition C0 is that the sequence of the Weiss symbol of the projection weakly converge to something. Okay? A level up of condition C0 is that the sequence converges in L2. Okay? It's of course a stronger assumption that we can. Another condition is that the sequence of the Weiss symbol of the truncated Hamiltonian is bounded in L2. And another level up condition is C1 prime, is that the sequence of the norm, the L2 norm of this Weiss symbol converges exactly to the L2 norm of the limit that we expect. Okay, so f times the limit of the sequence. Finally, this is the condition C2 is a condition that that guarantees that we can neglect the part related to the commutator in the previous slide. And so it says that we require that the L2 norm of the Weiss symbol of the orthogonal projection with respect to Pn. So I is the identity. So I minus Pn is the projection on the complement in the event space. So the Weiss symbol of this part in L2, the norm converges. Okay, and this is a condition that it is needed in the proof, and that is satisfied in all the examples that we are analyzed, but typically is hard to check. Okay, so now that I stated some conditions, some possible conditions, let us now look at the T. So what is the T? The theorem is that if mu is positive and H is the quantization of a certain function f, and if f is, we analyze two possible classes of functions that we can quantize. So the first one is a function that do not mix x and So it's the sum of the function of x and the function of p, or function that mix x and p, but for instance they are polynomial in p, and the coefficients are infinity with the polynomially bounded, are polynomially bounded. Okay, so we allow these two kind of functions for the quantization for the operator. For instance, all the Schrödinger operators are okay. Okay, and also okay, I will explain later examples. So if f is one of these two possible choices, if conditions C0, C1, and C2, namely if the sequence of the byte symbol of the projection weakly converge, if the sequence of the byte symbols of the Hamiltonian, truncated Hamiltonian is bounded, and if the condition is hard to check, of course, then the sequences of the byte symbol of the truncated Hamiltonian weakly converge. If one replaces condition T1 with the level up, so with the, if we assume that we have the strong convergence in L2 of the byte symbol of the projections, then, sorry, not the projection. So if we have that the byte symbol, the L2 norm of the byte symbol of the Hamiltonians converges to the norm of the limit, then of course one obtains the L2 convergence of this. Okay. Yes. No. So this is d equal 1 just for simplicity. Okay.
So if I understood well, so condition C2 is exactly what we need when you write down this commutator, but we found a different inside. So what does it mean from the physical?
Because the point is that you have the operator of Hn is Pn Hn. Okay, so you have two products here. So the symbols should be the bytes, the Moyer product of these times the symbol of these times the symbol of this, and all these Moyer products are integral that can consider in terms. So in order to not control really these all these integrals, the condition on the commutator reduces the difficulty. Okay. Otherwise, since you have the two parameters, so the dimension and h bar, everything that is strongly dependent on n and h bar.
It's purely algebraic, the way you understand.
Yeah.
So, but in some special cases, you can give a physical interpretation, no? Because it's by n projection on a bounded region of the rotational space. Then you say localize and measure energy, and the question is how probable is that the particle is.
Yeah.
And of course, you have to,
Yeah,
to
you have
make
to be,
assumptions
yeah,
on parity.
yeah.
So the symbol PM starts with some known symbol class that you want to establish.
Yes, the point is that the symbol may also be infinity, but you are considering n to infinity. So at the end, it becomes discontinuous because you have in mind that this is a characteristic function. You lose every regularity, and the regularity is very important when you perform semi-classical. Okay, so I want to come back to condition C0. So exactly this part. So what is the limit of the byte symbol of the projection? As I said, it is real that in the limit you obtain the characteristic function of a certain bounded domain omega, at least if one consider a Schrödinger operator, so p squared plus b, where b is a confining potential, so it's a regular potential confining, and so this operator is self-adjoint, is essentially self-adjoint, and has a eigenvalues accumulated at infinity and so on, and it is very well known. And so one can consider the family of the spectral projection of A, okay? And one can consider this kind of projection, okay? So using a spectral calculus, one functional calculus, one can write down is in this way, okay? So EK is the sequence of the eigenvalues, okay? So we can state theorem 2. So about the limit of this bisymbol of the projection. So if mu is positive, then by law, I mean the sequence of eigenvalue converging the limit n to infinity and h bar to 0 with h bar times n equal to mu to a certain value e, that is depending on mu and is the solution of this equation. Okay, so this is the classically allowed region at the level E. Okay, and under this condition, condition C0 prime holds, namely the sequence of the bisymbol of the projection converge exactly to the characteristic function of this classically allowed region, where this is the definition of. Okay, so you can say that here is 1/2 of p squared plus p, that is exactly the classical Hamiltonian associated to the Schrödinger. Oh, so a very trivial remark is that condition C prime imply condition C0. So with this theorem, we have a large class of family of orthogonal projection that realize condition C0 and given C0. Okay. So now I want to look at an example. Okay, let us look at a model, a specific model to which we can apply our procedure. Okay, so we consider the Hermite function, and in the case of Raymonde collaborators. So we consider the projection on the first n Hermite wave functions. And okay, so the eigenvalues are the one of the oscillator. And okay, so it's very easy to compute what is the limit of this sequence. That is, of course, exactly 2. And the classically allowed region is a disk in phase space with center in 0 and the radius square root of 2. And so from theorem 2, we know that the symbol of projections converges in L2 to the characteristic function of this. So what about the Hamiltonian that we want to truncate using this kind of projection? So we consider this kind of Hamiltonian that are the quantization of a polynomial next to it. Okay. So for instance, when a is equal to 0 and b equal to 1 and n is equal to 1, we end up with the momentum. That is exactly the model considered by Raymond and collaborator in the cavity electrodynamics. Okay? And so we can consider this truncated Hamiltonian, this Dino Hamiltonian. And okay, we can, yeah, everything can be computed because it's harmonic oscillator, position, momentum, everything is very explicit. And so one can look at this finite rank operator as a matrix representation in the basis of Hermite. And this is a finite band matrix. Okay, so for instance, if n equal to 1, and if we consider only the momentum operator, we have a 3-diagonal. Okay? And so this example, I like very much this example because we can use a combinatorial procedure, in order to prove that the L2 norm of these by symbols of this truncated Hamiltonian converge exactly to the L2 norm of the limit. Okay, they enter Catalan numbers and path, and it's nice. And also condition C2 using these combinatorial techniques is satisfied. And so for this model, we are able to show that since condition C0 holds, because they are spectral projection of Schrödinger operator. Condition C1 prime holds, condition C2 holds, then so the limit holds in the stronger edges.
This higher dimension still works.
Yeah. We didn't try, but I think. Okay, so let us now look at another example. Another example that escape from theorem 2. So the theorem that guarantees the convergence of the limit of the projection. Okay, because now we are considering an operator A that is not a Schrödinger operator. It is the Laplacian in an interval minus n with Dirichlet boundary. Okay, so of course this is not a Schrödinger operator because the potential is infinite or 0. So it escaped from the previous example. But here everything is explicit, the model is integrable, so we can compute eigenvalues and eigenvectors. These are the eigenvectors, these are the eigenvalues, and we can consider the projection ion using these eigenvalues. Okay, so again, if mu is fixed, then we can compute the limit of the eigenvalue, and they are explicit, so we obtain is the value of the energy, E, that is again related to mu. But okay, so we are not able to use theorem 2, but using different techniques that of course are model dependent, we were able to prove the L2 convergence of this bi-symbol of the projection to the characteristic function of the classically allowed region. That is in this case a rectangle. Okay, this is I mean this is folklore for certain, but we were able to. In this case, so this is exactly this rectangle in the space.
Obviously, it's independent of the boundary conditions.
No,
So
yeah.
prime and the rest because you just only have the larger values. So, yeah.
Okay, so we consider with this projection two kinds of operators that we can truncate using this projection. So the first one is a multiplication operator. So it's a function, a multiplication with this kind of function. Okay, and this is not this is one possibility, but this possibility is the one that gives this matrix, the representation of this matrix exactly tridiagonal as the momentum truncated on the eigenvalues of the harmonic oscillator. So we are able to use similar techniques in this case, and these are related to Chebyshev polynomial. And another kind of possibility is to consider the momentum. Okay, so only the momentum. And this case is very hard. So this model is very hard because the matrix associated to this Hamiltonian in the basis of Pn is not a finite dimension matrix. So it's a full matrix. You see, it's a chess matrix, but it is full. And so this complicates a lot the control because you lose the fact that the commutator is finite round.
So you don't understand the moment. What is the momentum on the interval?
No. The momentum is on all the real.
Okay.
And you truncate the momentum on the eigenvalue on the first n levels of the Dirichlet Laplacian in the because this is exactly the part of our theory that tells us that the model is triggered because the projection and the operator commute. This is exactly not the Okay. So, as I said, this model, this is the part that has been studied with our master student that works very, very much, and actually she changed words now. It's not in PhD, maybe too difficult. Okay, but okay. So, using totally different techniques, we were able to prove for these two kind of truncated observables the L2 convergence of the line symbol of the truncated Hamiltonian to f times the characteristic function of the classical analog. Okay, so summarizing what we were able to do is to consider projection, to consider Hamiltonians, to truncate this Hamiltonian with final trunk projection, and to provide some assumption that guarantees that the byte symbols converge, for instance, in L2 to a certain limit. Okay. Okay. So now the question is, what happened to the dynamics, the quantum dynamics generated by this Hamiltonian, by HM, in the limit, in the same classifier? Always in this limit, h bar to 0 and to infinity with the product x. Well, okay, so this is the Hamiltonian, this is the Schrödinger equation with this Hamiltonian. So this is the initial state that we assume is in the range of the projection. We normalize. Then we can describe, as I said, this Schrödinger equation in phase space in terms of eigenfunction. So this is the equation written in terms of the eigenfunction. So where here this bracket is the Moyal bracket, namely it is the Moyal product of the first term times the second minus the Moyal product with the opposite order. Okay? So this equation, everything in this equation depends on n and on h bar. So it is a very complicated equation to start with. Okay? So what happens to the solution of this equation when h bar to 0 and to infinity with the product? Okay, so it is known that the Moyal bracket divided by EH bar behaves like Poisson bracket, where H bar is small. We know that the byte symbols have a limit that is a sort of classical Hamiltonian function, H. We assume that the initial state has a limit, so for instance, that they concentrate in x0 and b0, so points in the space, with x0 and b0 in the classically allowed region, omega. So one could expect that the dynamics, the classical dynamics, is given in terms of Hamilton equation associated to the Hamiltonian function H, with this initial function for x0 and okay, so let us now look at a specific example, not in general. So let us look at example 1, that is, as I said, the one considered in the experiment. So it's the truncation of the momentum on the n, on the first n levels of the harmonics. So we consider h, that is the momentum. So here n is equal to 1, a is equal to 0, and b is equal to 1. So h is the momentum, and pn are this projection. Okay, so as we said, the classically allowed region is a disk of radius square root of mu. So the Hamiltonian, the classical Hamiltonian is P, is the symbol of H, times the characteristic function. And here you can say a plot of this byte symbol in phase space. So here n is 17 and mu is 2, and up to this oscillation, you see that this is a tilt coin. Is P cut on the disk. Okay. Okay. So as we already said, we expect Hamilton equation with that Hamiltonian, but what is the problem here? Is that this Hamiltonian is discontinuous. So it is not possible to write down Hamilton equation with a discontinuous Hamiltonian. Okay, but we want to insist in this direction, so we write down the Hamilton equation, at least formally, and we end up with these two equations that have a part that is irregular when the points are inside omega, plus a term that depends on the fact that the Hamilton is discontinuous. So it appears that okay, so R here is the square root of x squared plus p squared, and of course the discontinuity happens. So here this is the space x p. So here it is mu. So the problem is when f is equal to. Okay, exactly this. Okay. So the Hamiltonian vector field is discontinuous at the boundary of omega. And so it is difficult to study this kind of Hamilton equation. But okay, let's try to see something about the phase portrait of this Hamilton system. So if we start with that zero is zero inside the disk, so if so assume that this is x0 is 0. Okay, so what happened to the equation that since we are inside the disk, the equations are very simple, x dot equal to 1 and p dot is equal to 0. So the particle moves on straight line until the particle reaches the boundary. Okay? So when the particle touches the boundary, what happens is that heuristically, in the previous equation, the dominant part will be this one. Okay, so the one proportional to the delta distribution. So equations are more or less this one, and heuristically this corresponds to a tangential field boundary. So the particle moves in this way down the boundary with infinite speed, and it reappears here, and it continues with the simple. So it is what on the physically expected time. So this is exactly what I said. So it's an explanation. So what happens is that these dynamics, in a sense, realize an identification of this point, so the point here, with the point. So what happens is that the collision at the edge realizes a reflection on this axis. And so in the limit, we observe a change of topology. So a motion on a plane becomes a motion on a sphere.
But how much time does it take to cross the diameter? Final time?
Yeah, time. The time to go from here to here is easy. Okay, so this is very heuristic, but this is exactly what the physicists observed in the experiment. Here I didn't mention that n is equal to 5, so it's not infinite. And so these numbers here are times. So this is a snapshot of the dynamics of the field inside the cavity. So this is the vector function at initial time. So it is inside localized inside the disk. So it evolves on horizontal line. So when touch the boundary, there is this interference part inside, but the mass is very fast here, and it reappears. So here n is equal to 5. Okay.
Would you increase the number n equals 5, expect as many blues and reds?
Sorry?
So the number of reds and blues you have is 5.
No, 25 is time.
Yeah, I understand.
Yeah.
The
The number of oscillations, of course, because all these I didn't say this. This limit that holds in L2 tell us that of course there is a subsequence that is complex convergent, but the object do not converge in a quantized sense because there are a lot of oscillations. Okay. And if you increase the number of n and you simultaneously send each back to 0, then of course it's exactly what we do. So the oscillation
how complex the thing. We will increase the number of postulations, how complicated they are now, depending on that.
I don't know, because really we didn't touch the aspect of dynamics from the quantum kind.
Yeah, I guess. It looks very much that you create some kind of pattern there. So, you will have very good.
Yeah. We didn't try.
This is
Yeah.
lens, but
Yeah, this is an experiment. So this is the Wigner function. So this is the Wigner function of the field.
one dimension.
One dimension.
Horizontal axis X.
X and the vertical axis is exactly this picture. So that, but we are not considering a point, but we are considering a density. Okay, so the Wigner function is essentially this, but it is not the positive, so it has a negative part and a positive. Yeah.
So there is a region where you only see essentially three and where in 20 you can say you see 5 are not completed, right? There are two groups that are not completed here.
You are counting this part,
Yes.
part.
However, there is a time when you really see.
Yeah, this is the part where the mass is touching the bound, and you don't see anymore this kind of blue band when it's escaped from this.
Question is whether the fact that there are exactly so many peaks as
yeah.
an function is a student that does not.
I don't know. No, this really I don't know.
It would be nice.
Yeah, I could agree with you. We have to take care of this stuff. Okay, so we want to really understand what happens from the mathematical point of view to the lead. So a natural question is to say, okay, we have a limited it is discontinuous at the boundary, but maybe there is a sort of approximation of a refined symptotic of this characteristic function near the boundary, namely a microscopically near the boundary, that maybe can help us to understand what is the dynamics. Okay? And we proved the following theorem that so the sequence of the projection, the right symbol of the projection, is near to a modification of the characteristic function, so it is a infinity function. So the difference is small when it is computing again test functions that are concentrating near the boundary. So here G is every infinite function with compact support, and we evaluated, we rescale this G with this power of H bar. So this part, this term is concentrating on the disk, on the boundary of the disk. So this difference against this kind of test function that are concentrating, in the limit, this difference is. Okay. The same object, the same behavior happens to the by symbol of the truncated Hamiltonian, where again we are substituting P, that is the by symbol of the Hamiltonian, and here again the same modification of the characteristic function. It is not whatever modification, it is a specific modification, and it is related to the Airy function. So the Airy function is this one, is AI. We consider the integrated Airy function. We rescale this Airy function with n, so we have something that depends on n, and this is exactly the modification that we do, the refined asymptotics near the boundary of omega. Okay, so this is the infinity function, and it converges pointwise to the characteristic function up to the boundary. Okay, it's radially symmetric, and at the boundary, orolenic is equal to 1/3. Okay, and so we can write down what is the Hamilton, the sequence of Hamilton equations with this modified Hamilton function. Now everything is very under control because everything is smooth. And you can see here the phase portrait, the trajectories associated to this function, this Hamiltonian function. And you can see that is very different with the one of the total Y symbol that contains many oscillations, so the orbits are very, very difficult to understand. So here n is equal to 7, so it's not so large, but you can see that more or less the orbit produces this kind of symbol, phase portrait. And another information that we have is that with this modified Hamiltonian, the speed of points near the boundary scales like n to the power of 2. So we have also quantitative information about the speed that becomes infinite. Okay, so some take-home message. First of all, I want to stress that quantum xenodynamics and quantum xeno effect are purely quantum phenomena. So we have to be very careful when we talk about the classical limit, but interesting properties can emerge when we consider non-standard limit. And another thing that I want to stress is that when we consider this semi-classical limit, the dynamics, in the dynamics we observe the change of topology, sort of a presence of boundary condition at the boundary. And so this is something that, in my opinion, is interesting. So some open problem is the first is we would like to address the semi-classical limit of the two quantum dynamics, namely the one with the Moyal product, the Moyal bracket, sorry, because it's not completely clear the fact that you can erase you can only consider quantum structure. Okay, so it's not the totally rigorous part. And other things that we are trying to study is the situation where the classically allowed region admits holes or is not convex. So we are able to create a projection that converges to, I don't know, something like this or many. So it could be interesting to study the dynamics of this kind of object. And finally, here we found a periodic boundary condition, this kind of object. Also in the one with the Dirichlet Laplacian was the same, but we are trying to understand if we can generate other classical boundary conditions in the classical Hamilton condition. And that's it. So I finished. So thank you for your attention.
Thank you so much, Marilena, for your talk. And are there any questions or comments?
So it was about the data function, because if I would like to do it on the big modifier.
Yeah, I mean the derivative function becomes is natural when you look at spectral projection of, for instance, Hermite, because is something related to universality of this Christophe Darboux. When you consider asymptotics near the singularity of Hermite, you always get here. But just a comment, we many years ago with a student, we considered the singular Hamilton equation with that singular Hamiltonian function, and we proved, but we didn't publish this paper, that if you consider any modification, you end up with this kind of solution in the limit.
Because it is usually arbitrary from the Hamiltonian system itself that should jump as related to the reflection point.
Yeah, the fact that it jumps, it depends on the fact that the velocity becomes infinite.
Yeah,
The fact, no, because if you look at I'm not able to perform a very nice. So this is a fact, okay? of this tilted coin, okay? So this is, so I show this picture, okay? This is a tilted coin. So this is a section, okay? So if you modify, you have that you fix the energy. So the trajectory must be on the level set of this energy. So this was exactly on this. So it cannot jump everywhere. It jumps exactly